this lesson, we are going to learn how to determine empirical formula of a compound. The abbreviation for empirical formula is EF. First of all, empirical formula of a compound shows the simplest whole ratios numbers of atoms of each element in the compound. When we look at the word simplest, think of the word lowest. So what is the lowest whole number ratios of atoms? An example of empirical formula is CH2O. Notice how the subscript cannot be simplified anymore because carbon has 1, there are 2 hydrogen and 1 oxygen. In order to understand empirical formula, we also need to look at chemical formula that are not empirical formula. For example, we have C2H4O2. Notice how we have 2, 4, 2. This subscripts can be simplified by dividing all of them by 2. If I divide this by 2, that would give me 1. If I divide this by 2, that would give me 2. And if I divide this by 2, that would give me 1. And this is not an empirical formula, where this one is. Let's look at another example. Here we have C6H12O6. And of course we can simplify this by dividing all of them by 6. Now, does this mean that these are not actual chemical formula? No. Again, these are just used to tell you that there are chemicals that have chemical formula that are very alike, but the subscripts are different. So the ratios of atoms in the compound are different, and therefore they are actually different compounds in reality. And they have different chemical properties as well, different physical properties. C6H12O6, that is glucose. That's the simplest form of sugar in our body. So what are the steps of determining the empirical formula? First of all, we need the total mass of each element in a compound. In most cases, basically they give you percentage and you have to convert percentage to mass. By assuming that the sample is 100 grams, when you assume the sample is 100 grams, you can convert percent by mass to grams because percent is always out of 100. And once you get your mass, we need to convert back to mole because our ratio are expressed in mole. Okay? And once we get our moles from our mass, we have to divide each of the mole by the smallest number of moles because we need to compare the moles in terms of a relative number, which is the smallest number. Now, the only thing that's tricky is when you have your ratios in terms of moles, you have a fraction like 0.5, 0.33, 0.25. You need to multiply by a number such as 2, 3, or 4 to remove the fraction. How does that work? 0.5 is equal to 1/2. So you multiply that by 2. Notice how the 2 cancel out, give you that number, right? Or simplify it to give you that number. And we have 0.33 that gives us 1/3. So multiply by 3. This simplify equal to 1 give us that. Notice how the 3 cancel out. Then we have 0.25, that's equal to 1/4, and we multiply that by 4. Notice how the 4 cancel out, give us that number. And we will multiply this to all of the ratios between moles. Let's do an example problems. A hydrocarbon compound contains 83.6% carbon and 16.4% hydrogen by mass. What is the empirical formula for this hydrocarbon? What is hydrocarbon? Hydrocarbon is basically a compound consists of hydrogen and carbon, sometimes oxygen as well. So let's look at this. First of all, we have percentage, right? And we can convert those percentages to mass by assuming that this sample is out of 100 grams. So here I have the format laid out. I have percentage for carbon and percentage for hydrogen. And if we assume that this is out of 100 grams, we can actually remove this percentage and then we have our grams of carbon and hydrogen. So again, this is assuming or assume out of 100 to give us that percentage to gram. So once we have our grams in terms of carbon and hydrogen, of course we can now convert to mole, because that is step 2 right there. Okay, convert to moles. And that's pretty easy. We just find the molar mass conversion factor. So here I have the molar mass for carbon, and I have the molar mass for hydrogen. Notice how the gram is on the bottom to cancel out. Same thing for hydrogen, we cancel that out, and that will give us our number of moles. Let's do the number of moles for carbon first. I plug in the calculator, I have 6.96 moles of carbon, and then for the hydrogen, I plug into the calculator, and I have 16.24 mole. And if we look at the steps, step 3 basically divide each mole by the smallest number of moles. In this case, what is the smallest one? Or the smaller one is this one. So this one divided by itself gives us 1. And this one divided by 6.96, which is the smaller mole, or the smallest in this case. And that gives us the ratios in terms of mole. We have 2.33. That tells you that there are C1, H 2.33. But going back to our empirical formula definition, we need a whole number ratio. This is not a whole number. 2.33 is not a whole number. So what we need to do is to get rid of this decimal somehow. And going back to our shortcut, when we have a decimal 0.33, that is equal to 1/3. And to cancel out the 1/3, we multiply them by 3. So what we have to do is multiply this by 3 and this by 3. The whole entire ratio by 3. Or basically multiply this by 3. Okay? And that will give us 3 carbon. And 2.33 times 3, that gives us 7. Or if we can multiply and distribute right there, it's the same method right there. So our answer is C3H7. This is our empirical formula. Let's try another example. A hydrocarbon compound again contains 75% carbon and 25% hydrogen by mass. What is the empirical formula for this hydrocarbon? Again, I have my percentage for carbon and hydrogen. And what can we do to change this percentage to mass? We have to assume that this sample is out of 100 grams. And when we do that, all we have to do is take this and take the percentage and just change it to grams. Notice how we have 25.0% equal to 25 grams of hydrogen. And for carbon, 75% becomes 75 grams of carbon. And we have gram. What's the next step we have to do? Of course, we have to go back to step 2 and convert it to moles, which is using the molar mass ratios. And I use a periodic table again. This is the molar mass for carbon, the same thing we did before, and this is the molar mass for hydrogen. The grams on the bottom to cancel out. And if I plug this into a calculator, 75.0 divided by 12.01 gives us 6.24 moles of carbon. And then for the hydrogen, I plug into the calculator, that gives me 20.75 moles of hydrogen. And if we go back to step 3, divide each mole by the smallest number of moles. Which one is the smallest one, or the smaller? Of course this one. So we have to divide all the moles by this smallest number, 6.24, that gives us 1. And over here, 6.24, that gives us 3.96. And of course we can round this to 4. So therefore we have C1H4. But we don't write the 1, so that gives us CH4. And this is the methane gas. Now let's try a more complicated problems. In this case, I have a samples of 5.44 grams was analyzed and found to have 2.5 grams of and 1.95 grams of oxygen and 0.94 grams of phosphorus. What is the empirical formula for this pure substance? First of all, we are not given percentage, but even more beautiful, we are given in terms of mass. So we don't have to assume anything about that the sample is out of 100 because we are given mass already. So what we have to do is go straight to step 2 and convert our mass to mole. So that was pretty easy. So I have this layout for you ready. I have the mass for iron, the mass for oxygen, and the mass for phosphorus. And to convert from mass to mole, we just multiply by the molar mass conversion factor. Of course, I have the grams on the bottom to cancel the grams out. And then if we plug this into a calculator, I have 0.0457. And if I do to the other one, I have 0.122. And if I do to phosphorus one, 0.0304. And going back to step 3, we have to divide by the smallest number of moles, which is this one right here. So this divided by the smallest number, which is itself, that will give us 1. And this will be divided by the smallest number again. We have 0.4. And again, divided by the smallest number. For this one, it turned out to give us 4.01. And for this one, it turned out to give us 1.50. Notice how we have the 0.5 right there. So again, we have to go back and think in terms of how do I get rid of this fraction 0.5? 0.5 is equal to 1/2, so we have to multiply everything by 2. Because right now, if we were to interpret this in terms of a chemical formula, we would have Fe 1.5, and oxygen would be 4 or in this case, just 4, and then we have phosphorus would be just 1. But that right there is not a whole number, so we have to multiply them all by 2, so that turned out to give us, let's just show this right here. Let's show this that we have to multiply them all by 2. I'm going to do that right here, okay? Multiply them by 2. Because we need to get rid of this 0.5. And that gave us 3. And for right here, that gave us 8. And for phosphorus, we want them to give us 2. And if we go back and do the same thing, we just distribute in here. And of course, for Fe, that will give us 3. For oxygen, that will give us 8. And for phosphorus, that will give us 2. Let's try another challenging problem. A hydrocarbon compound contains carbon and hydrogen. A scientist discovered that the compound has 25% hydrogen by mass. What is the empirical formula for this hydrogen carbon? And if we look at this problem, notice how we are only given the percentage for hydrogen. What about carbon? But let's go back and think about our math skill. First of all, this compound contains 2 elements. And we know that percentage is out of 100. So if I know the values of 1, of course I know the other values as well. Let's look at the problem. First of all, again, we have this compound contain carbon and hydrogen. And I know that carbon plus hydrogen in terms of percentage by mass give me 100. So if I figured out that hydrogen is 25%, can I just solve for carbon as a variable of x? Of course, that's easy. Carbon is equal to 100 minus 25, and of course that gives us 75% by mass for carbon. And then we have again for hydrogen, which is 25%, and if we assume that this sample is out of 100, we have 25 grams of hydrogen, and going back here for carbon is 75%, so we have 75 grams of carbon. And the next step, step 2, is convert to mole using the molar mass. And notice how I put the grams on the bottom to cancel out. And for hydrogen, I have 24.75. And for carbon, I have 6.24. So what is the lowest number of moles? Of course, this one. So I have to divide all the moles by that lowest number. 6.24. 6.24. And this gives us 1. And this, if we plug it into a calculator, that gives us 3.96, which is about 4. So we have CH4. And that is our answer.